Welcome. Take a moment to settle in without trying to find the perfect position. Turn the volume down to the point where my voice is only just audible, a little below what would be comfortable in daylight. Nothing that follows needs to be remembered or understood or followed to the end. You can fall asleep at any point, and you will not miss a thing. Tonight we are going to talk about the Voyager probes. 100 facts to fall asleep. To know adverts slowly without hurrying. The 4 large planets of the outer solar system move at their own unhurried rates, and the difference between those rates is what governs everything that follows. Jupiter completes a circuit of the Sun in a little under 12 years, Saturn in about 29.5, Uranus in roughly 84, and Neptune in something close to 165. Because their periods have no simple ratio between them, their positions around the Sun drift in and out of agreement, and for most of any given century they are scattered across the sky, one in the evening quarter, another far around behind the Sun, a third somewhere in between. The arrangement that matters for a spacecraft is not a straight line, which never quite happens, but a gentler thing, a spread of the 4 planets across a manageable arc of their orbits, each one arriving at the right place at the right moment to hand a small robotic visitor onward to the next. That kind of loose gathering was due in the second half of the 1970s, and it was calculated to be the sort of arrangement that comes around only once in about 176 years. A figure often quoted because it reflects how long the 4 planets take to return to a similar relative spread. The previous occasion had passed unremarked in the 18th century, when no instrument existed that could have made use of it, and Neptune had not yet been recognized as a planet at all. The next would fall well beyond the lifetime of anyone who worked on the mission. The window was therefore not an opportunity that could be deferred to a better funded decade, and everyone involved understood that the schedule was being set by the planets rather than by any committee. The reason the arrangement mattered comes down to the difficulty of moving away from the Sun. A rocket leaving Earth for the outer solar system is climbing continuously against the Sun's gravity, losing speed as it rises, and the further out the destination lies, the more launch energy is required, or the longer the journey becomes. A direct flight to Neptune using the chemical rockets available in the 1970s would have taken something on the order of 30 years. With a spacecraft so small and so slow that little of value could be carried, and with an arrival date so distant that most of the engineers who built it would never see the data. The mathematics of that problem had been understood since the earliest days of orbital mechanics, and for a long time it seemed to close off the far planets entirely. The escape from that arithmetic lies in the fact that the planets themselves are moving, and moving quickly. A spacecraft passing close to a planet is pulled into a curved path by that planet's gravity, and when it departs, it is traveling at the same speed relative to the planet as when it arrived, but in a different direction. Relative to the Sun, which is the frame that matters for the rest of the journey, the change is not merely one of direction. If the pass is arranged so that the spacecraft leaves in a direction that shares more of the planet's own motion around the Sun, it carries away a portion of that motion as extra speed, and it can be flung outward on a wider and faster orbit than the one it arrived on. Momentum is conserved throughout, so the planet is slowed by an equal and opposite amount. Though the exchange is so lopsided in mass that the effect on the planet is far too small ever to be detected. The technique came to be called the gravity assist, or sometimes the slingshot, and its careful working out belongs to the early 1960s. A graduate student named Michael Minovich, then studying at the University of California and spending time at the Jet Propulsion Laboratory in Pasadena, set about computing numerical solutions to the problem of a small body moving under the gravity of the Sun and a planet at once, a problem with no tidy formula for its answers. The computers available to him were room-sized machines fed on punched cards, slow by any later standard, and the calculations consumed a great deal of their time. What emerged was a catalogue of trajectories showing that a spacecraft could be routed from planet to planet at little cost in fuel, using each encounter to reshape the path toward the next, and that journeys previously written off as impractical became a matter of arriving at the correct place on the correct date. A few years later, in the middle of the decade, another graduate student working at the same laboratory, Gary Flandreau, took up the specific question of reaching the outer planets and began plotting where Jupiter, Saturn, Uranus, and Neptune would be through the remainder of the century. The pattern he found was the one the planets had quietly been assembling for decades. A spacecraft launched from Earth in the second half of the 1970s could reach Jupiter, be turned and accelerated there, arrive at Saturn a few years later, be turned again, and continue to Uranus and then to Neptune, reaching the outermost of them in something like a dozen years, rather than the 30 that a direct flight would demand. The idea of stringing all four together in a single journey acquired a name in the years that followed, and people began to speak of a grand tour of the outer solar system. Between the calculation and the flight lay the question of whether the technique worked in practice, and that was settled in stages. Spacecraft had already used the Moon's gravity to alter their paths, and the principle was tested at planetary scale when a probe bound for Mercury was routed past Venus, using that passage to fall closer to the Sun than a direct launch would have allowed, and reaching Mercury in the middle of the 1970s. Meanwhile, a pair of earlier probes had been sent out toward Jupiter, crossing the asteroid belt to see whether the dust and debris there would destroy a spacecraft, and measuring the intensity of the radiation belts around Jupiter, which turned out to be fiercer than anticipated. One of those probes was itself turned by Jupiter toward Saturn, a demonstration in the outer solar system of exactly the maneuver the tour depended upon. The Grand Tour, as first proposed, was ambitious in its hardware as well as its route. Studies were made of a new class of spacecraft designed to survive a decade or more without maintenance, carrying computers able to detect their own faults and reconfigure around them, and the plan envisaged several launches covering different combinations of planets. The estimated cost was large. The federal budget of the early 1970s was under pressure from other commitments, and the full program was cancelled. What survived was a more modest proposal for 2 spacecraft to visit Jupiter and Saturn, approved under the name of an existing and well-tested family of planetary probes, and known for several years as Mariner Jupiter-Saturn 1977, before it was renamed Voyager a few months ahead of launch. The engineers who designed those 2 spacecraft, however, kept the wider possibility in view without ever formally promising it. The trajectory chosen for the second probe was selected so that, if the first one succeeded in its close examination of Saturn's largest moon, the second would be free to continue outward toward Uranus and Neptune, and the spacecraft themselves were built with a margin of reliability well beyond the 4 years needed to reach Saturn. Officially, the mission ended at Saturn. In practice, the option to carry on had been quietly preserved in the shape of the flight path and in the durability of the parts. The launch window itself was narrow, a matter of weeks in the late summer of 1977, because the geometry that permitted the tour also demanded that the spacecraft leave Earth at the moment when the whole sequence of arrivals would line up. Miss the window and the chain of encounters would break, first at Neptune, then at Uranus, and eventually the whole arrangement would drift apart for another century and 3/4. The 2 rockets that would carry the probes were prepared through the spring and summer, and the planets, indifferent to the schedule, went on drifting into the positions that had been foreseen more than a decade earlier by a young man with a plotting chart and a great deal of patience. The 2 spacecraft were built as twins, and that decision came less from sentiment than from arithmetic, since the reliability of any single machine sent to Jupiter could not be guaranteed, and the cheapest form of insurance was a second machine identical to the first, assembled from the same drawings, tested in the same chambers, and launched a few weeks apart. They inherited a lineage. The Jet Propulsion Laboratory had been building deep space probes since the early 1960s under the Mariner name, and the design that became Voyager began life as a project called Mariner Jupiter-Saturn, which was only renamed in the spring of 1977, a few months before launch. Much of the engineering vocabulary carried over from those earlier missions: the 3-axis stabilization, the star trackers, the articulated platform for the cameras, though almost every component had to be rethought for a journey measured in years rather than months. At the center of each spacecraft sits a 10-sided ring of aluminium, a decagonal bus a little under 2 meters across and less than half a meter deep, divided into compartments that hold the electronics. Inside that ring, filling the hollow core, is a spherical tank of hydrazine, and around the outside are the bays where the computers, the radio transmitters, the power conditioning equipment, and the data recorder are bolted into place. It is a simple arrangement, and it has a certain logic to it, because the heat generated by the electronics could be spread evenly around the ring and vented through louvres, while the propellant sat in the warmest part of the structure and never froze. Everything else on the spacecraft, the antenna, the booms, the generators, the instruments, hangs off that 10-sided frame. The most visible feature is the dish. Just under 4 meters in diameter, a parabolic reflector of honeycomb aluminium with a feed assembly at its focus. It dominates the spacecraft in every photograph, and for most of the mission, it has pointed steadily back toward Earth. The dish handles both the S-band and the X-band radio links, sending science data outward on the higher frequency and receiving commands on the lower, with a transmitter output measured in tens of watts, comparable to a household light bulb, which is the entire strength of the signal that has to cross the distance between the spacecraft and a receiving antenna on the ground. Behind the dish, a smaller low-gain antenna handles communication near Earth, where precise pointing matters less and the spacecraft is close enough for a broad, weak beam to be heard. Power was the constraint that shaped everything else. Beyond the asteroid belt, sunlight thins to the point where solar panels become impractical, since at Jupiter the sunlight is only a few % of what reaches Earth, and at Neptune it is roughly 1,000th. So each Voyager carries 3 radioisotope thermoelectric generators, cylindrical units mounted in line on a boom that holds them out and away from the sensitive instruments. Inside each one, pellets of plutonium dioxide give off heat as the plutonium decays, and that heat is converted directly into electricity by banks of thermocouples made from silicon-germanium alloys, with no moving parts, no fuel to burn, and nothing to wear out except the isotope itself. At launch, the three generators together produced something in the region of 470 watts. That figure was always going to fall. The plutonium isotope used has a half-life of a little under 88 years, so the heat supply declines slowly and predictably, and the thermocouples themselves degrade as well, which means the available power drops by a few watts every year without exception and without possibility of repair. The engineers knew this in the 1970s and built a power budget that stretched decades into the future, ranking instruments and heaters in the order they would eventually have to be switched off. Much of the mission operations work of the last 30 years has consisted of managing that slow decline, deciding which piece of equipment can be left cold, which heater can be turned off without the propellant lines freezing, and how to keep the transmitter fed. Movement is handled by hydrazine. 16 small thrusters, each producing less than a newton of thrust, are arranged in clusters around the spacecraft, half of them designated as the primary set and half as backups, and they work by passing liquid hydrazine over a catalyst bed where it decomposes into hot gas. The same propellant serves two purposes: holding the spacecraft steady against the tiny torques that would otherwise let it drift, and making the occasional trajectory correction, each one a matter of a few meters per second at most. Attitude is sensed by sun sensors and by a star tracker aimed at Canopus, a bright southern star chosen because it lies well away from the plane of the planets, so the spacecraft always has two independent references and can work out its orientation in 3 dimensions. 2 long booms extend from the bus. One, a few meters long, carries the science instruments and the steerable scan platform on which the cameras and the spectrometers are mounted, so that they can be pointed at a target while the antenna stays fixed on Earth. The other is far longer, a lattice of glass fiber and epoxy that was rolled up inside a canister for launch and then unfurled to a length of some 13 meters, and it carries the sensitive magnetometers out where the spacecraft's own electrical fields cannot confuse their readings. 2 further antennas, each about 10 meters long, are mounted at right angles for radio astronomy and plasma wave measurements. The whole assembly, folded for launch and opened afterwards, gives the spacecraft its slightly improvised silhouette. The computers are the part that surprises people who come to the story from a modern vantage point. Each Voyager carries 3 separate computing systems, each of them doubled for redundancy. One for command sequencing, one for handling and formatting science data, and one for attitude and articulation control. Their memories were built from plated wire and magnetic cores, technologies chosen because they hold their contents without power and tolerate radiation better than the alternatives available at the time. And the total storage across all 3 systems amounts to a few tens of kilobytes, less than the space taken up by a single ordinary photograph on a telephone today. Programs were written in assembly language and in machine code, laid out instruction by instruction, and every sequence had to be tested on the ground before being sent. Because there was no way to transmit data continuously from beyond Jupiter, And because a spacecraft racing past a planet gathers information much faster than it can send it home, each Voyager also carries a digital tape recorder, an 8-track machine capable of holding a few 100 million bits, roughly 100 images, which could be filled during a close encounter and then played back slowly over the following days. The tape moves on a reel, one of the very few moving mechanisms on board, and its longevity was a matter of some concern to the designers, who specified a robust transport and limited the number of times it would be used. Jupiter's radiation belts forced a late round of hardening. The Pioneer spacecraft that flew past Jupiter earlier in the decade had measured charged particle intensities well beyond what anyone had expected, and the Voyager teams responded by selecting more resistant electronic parts, wrapping cable bundles in metal foil, adding shielding around the most vulnerable assemblies, and rerouting wiring away from exposed positions. Thermal protection came from multi-layer blankets of aluminized plastic film, from small electric heaters, and from radioisotope heater units placed near components that had to stay warm, since a spacecraft in shadow at Saturn loses heat steadily and propellant that freezes in a line does not thaw. Assembly took place in clean rooms, in filtered air, with technicians in coveralls and gloves handling components that had been individually inspected and logged. Each spacecraft comprises something on the order of 65,000 separate parts, and each part carried its own paperwork, its own test history, its own record of who had touched it and when. The finished vehicles were shaken on vibration tables to simulate the ride on the rocket, baked and chilled in thermal vacuum chambers to simulate sunlight and shadow, and run through their command sequences again and again while engineers watched for the small anomalies that tend to precede large failures. Both weighed a little over 800 kilograms with propellant aboard, which is to say about as much as a small car, spread out into a shape that could only exist where there is no wind and no weight. 11 investigations were carried aboard each spacecraft, and together they weighed something on the order of 100 kilograms, which is to say roughly an eighth of the launch mass of the vehicle that carried them. They divided naturally into two families. The first family looked outward along a line of sight and needed to be pointed with care, gathering light and heat from planets and moons and rings, and these instruments were mounted together on a movable platform at the end of a boom. The second family did not look at anything in the ordinary sense, but instead sampled the space the spacecraft was passing through, counting particles, sensing magnetic fields, and listening to oscillations in the surrounding plasma. And these were fixed to the body of the craft or set out on booms and antennas of their own, since they had to be kept away from the electrical noise of the machine that carried them. The pointed instruments sat on a scan platform that could swing in two axes, in azimuth and in elevation, driven by geared actuators that turned in small increments and held their position while an exposure was made. 4 investigations rode on that platform. There were the 2 television cameras, there was an infrared interferometer and radiometer, there was an ultraviolet spectrometer, and there was a photopolarimeter, and because they were bolted to the same frame, they all looked in the same direction, so that a sequence of observations at a moon or a cloud band could be built up from several kinds of measurement of the same patch of sky. The imaging system used 2 cameras of different focal length, sharing a common design and mounted side by side. The narrow-angle camera had a focal length of about 1500 millimeters and a field of view of a fraction of a degree, and it did the work of a telescope, resolving the fine structure of cloud belts and the grooves on Ganymede. The wide-angle camera, with a focal length nearer 200 millimeters, took in a field roughly 10 times broader and was used for context, for crescents, for whole planets when they had grown too large for the narrow field. Neither camera used film or the solid-state sensors that came later. Each held a Vidicon tube, a small vacuum tube with a photoconductive target, on which an image was built as a pattern of electrical charge and then read off line by line by a scanning electron beam. The frame was 800 lines by 800 samples, giving 640,000 picture elements, each recorded at 8 bits of brightness, so a single image amounted to a little over 5 million bits of data. In front of each camera was a wheel of 8 filters, in clear and blue and green and orange and violet, and on the narrow-angle instrument, filters chosen for methane and sodium, so that color pictures had to be assembled on the ground from separate exposures taken through different glass, one after another, with the target moving slightly between them. The infrared instrument combined 2 functions in one housing. Its interferometer split the incoming infrared light, recombined it with a moving mirror, and recorded the interference pattern, from which a spectrum of thermal emission could be recovered on the ground. From those spectra came temperatures at different depths in the atmospheres of the giant planets, estimates of the proportion of helium to hydrogen, the identification of gases present in small quantities, and measurements of how much heat each planet radiated compared with how much sunlight it absorbed. A separate radiometer channel measured reflected sunlight over a broad band. The same instrument found the warm patches on Io that turned out to mark active volcanic centers, and it measured the temperature of Titan's haze and the chill of Triton's surface. The ultraviolet spectrometer worked at wavelengths far shorter than the eye can register, using a diffraction grating to spread the light across a row of detectors. Its main subjects were the faint glows of upper atmospheres, the auroras near the magnetic poles of Jupiter and Saturn, and the composition of thin gases that emit or absorb strongly in the ultraviolet, particularly hydrogen and helium. It was also used in occultation, watching a bright star or the sun itself pass behind the limb of a planet or behind a ring, and reading the structure of what lay between from the way the light dimmed and returned. Because it needed no illumination beyond the sky itself, it went on making observations during the long quiet stretches between planets. The photopolarimeter was the smallest of the pointed instruments, a modest telescope fitted with filters and with analyzers that admitted light of a particular polarization. Its purpose was to measure how the brightness and the polarization of scattered sunlight changed with viewing angle, which carries information about the size, shape, and texture of the particles doing the scattering, whether cloud droplets in an atmosphere, dust on a surface, or fragments in a ring. The instrument on one of the 2 spacecraft failed early and returned little, and the one on the other operated with restrictions for much of the mission, which is a reminder that the redundancy built into the engineering systems did not extend to every scientific instrument. Away from the platform, the magnetometers required something unusual: distance. 2 low-field magnetometers were carried on a boom that extended about 13 meters from the body of the spacecraft, folded before launch into a canister roughly a third of a meter long and unfurled by the stored energy in its own glass fiber lattice, so that the sensors could sit far out in space where the residual magnetism of the spacecraft itself was faint. One sensor was placed at the end of the boom and one partway along it, so that the spacecraft's own contribution could be estimated from the difference between them. 2 high-field magnetometers were mounted on the body, built to cope with the intense fields near Jupiter that would have saturated the sensitive instruments. Together they measured the strength and direction of the magnetic field along the whole flight path, mapping the shape of each planet's magnetosphere, revealing the tilted and offset fields of Uranus and Neptune, and following the weakening field of the Sun out to distances no instrument had reached before. The plasma instrument used Faraday cups, simple collectors that measure the current carried by charged particles entering through a grid, arranged so that one cluster faced roughly back toward the Sun and another looked to the side. From the currents at different retarding voltages came the density, speed, and temperature of the solar wind, and inside the magnetospheres the properties of the trapped and flowing plasma, including the ring of ionized sulfur and oxygen that Io leaves along its orbit. Above the energies the plasma instrument could reach, the low-energy charged particle detector took over, a set of solid-state telescopes mounted on a small platform that stepped around in stages so that the instrument could sample particles arriving from different directions, rather than only from one. At higher energies still, the cosmic ray system used stacks of silicon detectors to identify individual nuclei by the way they lost energy passing through successive layers, distinguishing not only elements but isotopes, and separating particles accelerated near the planets from those arriving from the galaxy at large. 2 whip antennas, each about 10 meters long and set at right angles to one another, served 2 investigations at once. The planetary radio astronomy experiment recorded natural radio emission across a wide range of frequencies, and from the regular pattern in that emission, the rotation period of a planet's deep interior could be worked out, which is how the rotation rates of Uranus and Neptune were established, since their visible cloud markings gave inconsistent answers. The plasma wave system used the same antennas at much lower frequencies to sense oscillations in the surrounding plasma, from which the density of electrons could be inferred, and it registered the impacts of dust grains as sharp bursts when the spacecraft crossed a ring plane. The 11th investigation carried no instrument of its own. Radio science used the spacecraft's own transmitter and the receiving antennas on Earth, measuring how the radio beam was bent, delayed, and attenuated as it passed through an atmosphere or a ring on its way to the ground, and how the frequency shifted as the spacecraft was pulled by the masses it flew past. From those shifts came the masses of moons and the internal structure they imply, and from the occultations came profiles of temperature and pressure in atmospheres and a measure of how much material each part of a ring contained. Bolted to the outside of each spacecraft, on the side of the bus that faces away from the antenna dish, there is a shallow aluminium case about the size of a dinner plate, and inside it a copper disc plated with gold. It is a phonograph record made by the same industrial process that pressed commercial records in the 1970s, and it carries sound and images cut as grooves into metal rather than written in any electronic memory. Nothing on the 2 probes was less necessary to their scientific mission, and nothing about them has been more often described. The idea had a modest precedent. The two Pioneer spacecraft that crossed the asteroid belt and passed Jupiter before Voyager each carried a small engraved plaque designed by Carl Sagan, Frank Drake, and Linda Salzman Sagan, showing a schematic of the solar system, a diagram of the hydrogen atom's lowest energy transition as a common unit of time and length, a map of the Sun's position with respect to 14 pulsars, and two human figures drawn beside an outline of the spacecraft itself. The plaque held only what could be scratched into a sheet of metal. When it became clear that the Voyagers would also leave the solar system, the question was whether something with more capacity could be carried within the mass and volume that the engineers were willing to give up, and a phonograph record, a technology already several decades old and well understood, turned out to fit. Sagan assembled a small committee to decide the contents, working with Frank Drake, the writer Timothy Ferris, the artist John Lomberg, Anne Druyan and Linda Salzman Sagan, and drawing on the advice of others, including the folklorist Alan Lomax, whose recordings and judgment shaped much of the musical selection. The whole project was compressed into a matter of weeks, since the launch dates were fixed by the positions of the planets and no schedule could be negotiated with Jupiter. Permissions had to be sought, tapes had to be located, translations had to be arranged, and the master had to be cut and plated in time to be mounted on spacecraft that were already being prepared for shipment to Florida. The disc plays from the outside inward at 16 2/3 revolutions per minute, half the speed of a standard long-playing record of the period, which doubled the playing time at some cost in fidelity. A cartridge and a stylus of the appropriate kind are included in the case, clamped beside the record. The aluminium cover is engraved with a set of diagrams meant to explain, without language, how the object works. One shows the record and the stylus in cross-section with the correct starting position. Another gives the rotation period, written in binary against the hydrogen transition as a reference clock, since a civilization capable of intercepting the spacecraft would know the frequency of that transition. A third shows how the video signals encoded on part of the disc should be assembled into a raster of lines to reconstruct a picture. And beside it, there is a drawing of the first image as it should appear if the instructions have been followed correctly, which is a plain circle. The pulsar map from the Pioneer plaques appears again on the cover, and in one small area, the aluminium was electroplated with a thin patch of uranium-238, whose decay gives a clock that could be read to estimate how long the record has been traveling. The recorded contents begin with spoken greetings in 55 languages, most of them contributed by members of the Cornell University community, each brief, most of them lasting only a few seconds. They range across widely spoken modern languages and include several that are no longer spoken at all, among them Sumerian, Akkadian and Hittite, reconstructed as well as scholarship allowed. There is no attempt at a common message. The greetings differ in what they say, some offering good wishes, some naming the speaker's place, some addressing whoever might be listening in terms of friendship. Alongside them, the record carries a written message from the President of the United States, Jimmy Carter, printed and attached to the spacecraft rather than recorded, and spoken remarks from the Secretary General of the United Nations, Kurt Waldheim. There is also a passage of humpback whale song placed near the human greetings rather than among the animal sounds, which was a deliberate decision by the committee. After the greetings comes a sequence assembled as a portrait of the planet in sound, running some minutes and moving through geological, biological, and human noises without narration. There are volcanoes, rain, surf and wind, thunder, crickets and frogs, birds, a hyena, an elephant, a chimpanzee, a dog, the sound of footsteps and a heartbeat, laughter, fire, tools being struck, a herding call, a horse and cart, a train, a tractor, a truck, a jet aircraft, the liftoff of a Saturn rocket, Morse code, the pulse of a pulsar, and the electrical signals of a human nervous system. Andrean's brain and heart activity were recorded and compressed into a short segment of sound near the end of that sequence, which on the finished record is an unremarkable rush of noise. One side of the disc carries 115 images plus the calibration circle, encoded not as pictures but as sound. Each line of each frame written as a varying tone in the same way that a television signal varies in voltage, so that the grooves themselves contain no visual information a listener could recognize. Color was achieved by sending 3 successive versions of the same scene through red, green, and blue filters, to be recombined by whoever decodes them. The selection begins with mathematics and physics, definitions of the units used, the chemical elements considered most relevant to life, the structure of DNA, and diagrams of cell division. It moves through the solar system, then to Earth, its continents seen from orbit, its landscapes and its coasts, its plants and animals, and then to people shown eating and drinking, licking, tasting, building, teaching, running, giving birth, and growing old. There are photographs of a supermarket, of a street in a city, of a house under construction, of the Taj Mahal, of the Golden Gate Bridge, of a radio telescope, and of a page of sheet music beside a violin, placed near the end as a bridge to the music that follows. That music runs about 90 minutes and holds 27 pieces. 3 of them are by Bach, the first movement of the second Brandenburg Concerto, the Gavotte en Rondeau from the third partita for solo violin, and the Prelude and Fugue in C-sharp major from the second book of the Well-Tempered Clavier, played by Glenn Gould. There is the first movement of Beethoven's Fifth Symphony, and the Cavatina from his 13th String Quartet, the Queen of the Night's second aria from Mozart's Magic Flute, and the Sacrificial Dance from Stravinsky's Rite of Spring. Beside those sit a court gamelan from Java, a percussion piece from Senegal, an initiation song of Mbuti women from the Congo forest, songs of Aboriginal Australia, the Mexican song El Cascabel, Johnny B. Good by Chuck Berry, a men's house song from New Guinea, a Japanese shakuhachi piece about cranes nesting, the Georgian choral song Chacrulo, panpipes and drum from Peru, Melancholy Blues by Louis Armstrong and his Hot 7, Azerbaijani Balaban music, a Bulgarian shepherd's song sung by Valia Balkanska, a Navajo night chant, an English galliard by Anthony Holborn, panpipes from the Solomon Islands, a Peruvian wedding song, the Gukin piece known as Flowing Streams, a raga sung by Kesabai Kirkar, and Blind Willie Johnson's Dark Was the Night, Cold Was the Ground. Some choices the committee wanted were not available in time or could not be cleared for use, and the list that exists is as much a record of what could be arranged in a few weeks as of what anyone thought definitive. In the blank space near the label of each disc, a short inscription was etched by hand, addressed to the makers of music in all worlds and all times. Beyond that, The record carries no explanation of itself, no key to its own selection, and no account of the reasoning that produced it. Its practical prospects were understood from the start to be slight, since the spacecraft are small, dark, and cold, and interstellar space is very empty, and neither probe is aimed at anything. What the gold plating and the sealed case did guarantee is duration. Away from atmosphere, water, and sunlight, with only occasional cosmic rays and the rare impact of a dust grain to wear at the metal, the grooves should remain legible for a very long time, longer than any archive kept on the surface of the Earth. Launch Complex 41 at Cape Canaveral had been built for the Titan rockets, and by the summer of 1977, it was the departure point for two spacecraft that had spent most of their design life under a different name, Mariner Jupiter Saturn, before being renamed only a few months before flight. The vehicle assigned to each was a Titan 3E with a Centaur upper stage, a combination that put a pair of solid boosters and two stages of hypergolic propellant beneath a hydrogen and oxygen stage capable of restarting in orbit. The Centaur was the delicate part of the arrangement, since liquid hydrogen must be kept extremely cold, and its tanks are thin enough to depend on internal pressure for their shape, and the whole stack, with the folded spacecraft and its solid rocket motor riding at the top under a fairing, stood taller than a 15-story building. Voyager 2 went first, on the 20th of August, 1977, because its trajectory was the slower of the two and its launch window opened earlier. That slower path was the one that could be bent at Jupiter and again at Saturn toward Uranus, and it required leaving Earth on a particular arc that would arrive at Jupiter in July of 1979. The ascent took the vehicle out over the Atlantic. The boosters and lower stages fell away on schedule. The Centaur placed the payload in a parking orbit and then reignited over the Indian Ocean for the burn that raised the path away from Earth, and after Centaur separation, the small solid motor bolted beneath the spacecraft, fired for about 3/4 of a minute to supply the last of the needed speed before it too was cast off. From that moment, the spacecraft had only its hydrazine thrusters, and everything else about the journey depended on gravity and arithmetic. The trouble began within the hour. The science boom, folded against the body of the spacecraft for launch, was commanded to swing out and lock, and the telemetry that should have reported the latch engaged did not report it. The engineers in Pasadena had no camera looking at the boom and no way to touch it, so they worked from what the spacecraft could tell them, which was mainly how it moved. A boom that had not locked would behave differently under thruster firings from one that had, and by studying the attitude data through the small maneuvers of the following weeks, and by comparing the pointing of instruments against known stars, they concluded that the boom had in fact reached its intended position and was very close to where the drawings said it should be. The latch indicator, not the latch, appeared to be the thing at fault. Alongside that, the spacecraft's own protective logic misbehaved in a way that was more unsettling to watch than it was dangerous. The deployment sequence involved sharp movements, and the attitude control system, reading those movements as symptoms of a failure, began switching to backup units and firing thrusters in patterns nobody had commanded, consuming propellant and confusing the telemetry stream. The onboard fault protection had been written to act quickly and without waiting for permission, which is the correct design for a spacecraft hours from Earth by radio, but it had been written with less imagination than the real launch supplied. Over the following weeks, the ground team rewrote the affected routines and sent them up, and the same lesson was applied to the second spacecraft still sitting on the pad, whose flight would be watched with the boom sequence in mind. Voyager 1 lifted off on the 5th of September 1977, 16 days after its twin, and its ascent came closer to failing than any other part of the mission. The Titan's first stage did not perform quite to specification, leaving a shortfall in speed that the Centaur had to make up, and the Centaur's guidance did precisely that, holding the engines running longer than the plan called for and shutting them down only when the required velocity had been reached. The margin left in the tanks when the engines stopped was a matter of a few seconds of burn time. The trajectory was correct, the spacecraft was healthy, and the analysis afterwards raised an uncomfortable point, since the same rocket, flying the heavier demands of Voyager 2's slower and longer departure path, would not have had that margin to spend. The order of the launches, chosen for reasons of celestial geometry, had turned out well. 2 weeks after leaving, on the 18th of September, Voyager 1 turned its cameras back toward home and took a set of frames that were combined into the first single photograph, showing the Earth and the Moon together in one field of view, both crescent-lit, at a distance of a little over 11 million kilometers. The image was made partly as a calibration exercise, since a camera that has just survived a launch needs to be checked against something whose brightness and geometry are known, and partly because the opportunity would not occur again. It shows the Moon smaller and dimmer than most people expect, and the space between the two bodies wide and unremarkable. Because Voyager 1 had been sent on the shorter and faster path, it gained ground steadily on its twin, and in the middle of December 1977, somewhere beyond the orbit of Mars, it passed Voyager 2 and took the lead it has held ever since. Both then entered the asteroid belt, a passage that occupied much of 1978 and that had been the subject of real concern a decade earlier, when nobody knew whether the region between Mars and Jupiter held enough small debris to shred a spacecraft. The Pioneer probes had already crossed it and survived, and their dust detectors had found the belt to be mostly empty, so the Voyagers went through it with attention rather than anxiety, at speeds that made avoidance meaningless in any case. Neither probe reported an impact of consequence, and the belt in practice was a region where the sunlight grew steadily weaker, and the instruments recorded the slow thinning of the solar wind. In April of 1978, Voyager 2 lost the use of its primary radio receiver. The spacecraft had gone for a stretch without receiving commands, and its onboard logic, following instructions written for exactly that circumstance, switched to the backup receiver on the assumption that something had gone wrong with the first. The backup had a fault of its own, a failed component in the circuit that tracks an incoming signal and follows it as its frequency drifts, so it could only hear commands sent within a very narrow band. Attempts to return to the primary receiver failed, and the primary then stopped working altogether, leaving the mission dependent on the deaf one. From that point, every command to Voyager 2 had to be transmitted at a frequency calculated in advance, accounting for the Doppler shift of a moving spacecraft, for the motion of the Earth, and for the temperature of the receiver itself, which shifted the band it could hear by a small amount for every degree of change. The ground team learned to predict all of this, and Voyager 2 has been commanded through that same backup receiver for the whole of its working life. The rest of the cruise was quiet in the way that long interplanetary flight generally is. There were trajectory correction maneuvers, each a matter of turning the spacecraft, firing thrusters for a measured interval, and confirming afterwards from the Doppler shift of the radio signal that the new path was the intended one. There were rehearsals in which the instruments were pointed and the scan platform exercised, and the encounter sequences run against a simulated Jupiter, so that faults would show up 2 years before they mattered, rather than during the few days when the planet would be in reach. The cosmic ray and plasma instruments took data continuously, mapping how the solar wind changed with distance from the Sun, and the ultraviolet spectrometers looked at stars. The photopolarimeter on Voyager 1 developed problems early and never worked well. By January of 1979, Jupiter had grown in Voyager 1's narrow-angle camera to the point where the images were better than anything obtainable from the ground, and a long observatory phase began in which the planet was photographed repeatedly over many rotations so that the motions of its clouds could be measured rather than merely described. The spacecraft was still tens of millions of kilometers out, closing at more than 10 kilometers per second, and the closest approach was set for the 5th of March, with Voyager 2 following 4 months behind on a path chosen to see the moons that its twin would not. The observatory phase produced something that had never existed before, which was a sequence of images of Jupiter closely spaced in time and consistent in geometry, and when these were assembled into short films, the atmosphere ceased to be a pattern of stripes and became a system of flows. The pale zones and dark belts, known since the 18th century, turned out to mark the boundaries of alternating winds, some blowing eastward and some westward, with speeds of well over 100 meters per second along the strongest jets. And the boundaries between them were unstable in a way that generated eddies continuously, small bright clouds spinning up along the shear lines, drifting, merging, and disappearing again over a few days. The whole circulation was driven far less by sunlight than the atmospheres of the inner planets are, and far more by heat leaking outward from the planet's interior, so that the pattern of winds held its shape over decades, while the individual features within it lived and died at a much faster rate. The great red spot resolved into a vortex rather than a stain. Its outer parts rotated counterclockwise, completing a circuit in something like 6 Earth days, and the material at its edge was moving at speeds comparable to the fastest jets nearby, while the center was comparatively still. Smaller clouds approaching from the east were caught in the circulation, carried around the periphery, and in some cases absorbed entirely, which suggested that the spot maintained itself in part by consuming the eddies that the surrounding winds delivered to it. The infrared instruments found the spot to be colder than its surroundings, which is the signature of clouds standing higher in the atmosphere, and so the feature was understood as a high, cold, anticyclonic dome of gas rising above the general cloud deck, wide enough that the Earth would fit inside it with room to spare, and old enough that observations of a spot at that latitude go back at least a century and a half. South of it lay 3 white ovals, smaller vortices of the same general kind, which had been watched from the ground since the 1930s. Elsewhere in the atmosphere, the infrared radiometer found openings in the cloud deck, regions the observers called hotspots, where the instrument was seeing down to warmer and deeper layers, and these turned out to be persistent features arranged along a particular latitude rather than random gaps. On the night side, with the cameras pointed at a Jupiter lit only by its own faint glow and by the light of its moons, Voyager 1 recorded flashes of lightning in the upper clouds, and the plasma wave instrument picked up the radio crackle that lightning produces, delivered as the low whistling tones that give such signals their name. The ultraviolet spectrometer found emission over both poles of the kind produced when charged particles rain down along magnetic field lines into an atmosphere, which is to say an aurora, on a planet whose magnetic field is by a wide margin the strongest of any in the solar system. A single long exposure taken during the Voyager 1 encounter, made from close to the plane of the planet's equator and planned as a deliberate search rather than as a general survey, showed a thin streak of light where no ring had been known to exist. It was faint, a few thousand kilometers wide, and startlingly thin, lying well inside the orbits of the large moons, and the following July, Voyager 2 was retargeted to look back at the same region from the far side, where sunlight passing through the ring would scatter forward off small particles and reveal material that reflected almost nothing when lit from behind the observer. That geometry showed the ring plainly and also showed a broad, tenuous halo of dust above and below it, and it established that the ring is composed largely of fine grains, which cannot last long in that environment and must therefore be replenished, most likely by dust knocked off small inner moons by micrometeorite impacts. Two of those moons were themselves found in the Voyager images by people who searched the frames specifically for faint moving points near the ring, and Amalthea, a small irregular body known since the end of the 19th century but never resolved, appeared as a lumpy, reddened object considerably longer than it was wide. Days before the first encounter, a short paper appeared in a scientific journal arguing that Io, locked in resonance with Europa and Ganymede, and therefore unable to settle into a perfectly circular orbit, would be flexed continuously by Jupiter's tides and heated internally to the point where its interior might be substantially molten, with volcanism at the surface as the likely consequence. The images arrived and showed a world of oranges, yellows, whites and blacks, mottled with dark spots and pale flows, and entirely without impact craters, which meant that the surface was being resurfaced faster than craters could accumulate. Then a member of the navigation team, working through a heavily brightened image taken a few days after closest approach in order to pick out background stars for orbit determination, noticed a crescent of light standing off the edge of Io's disk, and on examination, it proved to be a plume of material rising far above the surface and falling back in a wide arc. Once the search was on, 9 such plumes were identified in the Voyager 1 data, some of them rising hundreds of kilometers, together with dark calderas hotter than their surroundings by a considerable margin, and long flows spreading outward from vents. The erupted material appeared to be rich in sulfur and sulfur dioxide, which accounted for the colors, and the frost that settled out of the plumes accounted for the whitish deposits ringing the vents. Io also explained things that had been measured without being understood. The ultraviolet spectrometer mapped a torus of ionized sulfur and oxygen occupying Io's orbit, a donut of glowing plasma fed by the escaping products of the volcanism, and the fields and particles instruments traced an electrical connection between the Moon and Jupiter's polar regions, carrying a current measured in millions of amperes, which is bound up with the long-known fact that Jupiter's decametric radio emission varies with Io's orbital position. When Voyager 2 arrived 4 months later and looked again, most of the plumes were still erupting in the same places, but the largest of them had stopped, and the deposits around several vents had visibly changed shape, which established within a single year that the surface of Io alters on timescales a person can observe. Europa was seen only distantly by Voyager 1, and its turn came in July, when Voyager 2 passed within a few 100,000 kilometers and returned images of a surface unlike any other. It was bright, made of water ice, almost featureless in relief, with hardly any craters and no mountains worth the name, and it was crossed everywhere by dark lines, some of them thousands of kilometers long, running straight or in gentle curves and intersecting one another in generations, along with shorter arcs that curved back on themselves. The lines were interpreted as fractures in a shell of ice that had been filled from below with something darker, and the extreme flatness of the whole body suggested that the shell was thin, or warm, or floating, and the possibility of liquid water beneath it was raised at once, since the same tidal heating that ran Io's volcanoes would operate on Europa more gently. Ganymede, larger than the planet Mercury and the largest moon in the solar system, was divided into two kinds of landscape. Dark regions, heavily cratered and therefore ancient, were separated by broad swathes of lighter ground filled with parallel grooves and ridges, tens of kilometers across and hundreds long, which cut across the dark terrain and were younger than it. Bright rayed craters punched through both, and there were also pale circular patches with almost no relief, the ghosts of large craters that had relaxed away in ice too soft to hold a rim. Callisto, farther out and colder, had no grooved terrain at all, only craters upon craters to the limit of resolution, and one enormous concentric bullseye of rings surrounding a bright central patch, the frozen record of a very large impact spreading outward through the crust. The two spacecraft together returned something over 30,000 images of the Jupiter system, along with continuous records of a magnetosphere so large that its tail was found to stretch outward for hundreds of millions of kilometers, and having done so, they were flung onward by the planet's gravity toward Saturn, arriving there 20 and 25 months later, respectively, with the encounter sequences already being written. Saturn approached slowly in the cameras, growing from a bright oval with a line drawn through it into a banded globe, wearing a structure that no telescope on Earth had ever resolved into its parts. And by the late summer of 1980, the ring system was already breaking apart under the gaze of the narrow-angle camera into more divisions than the observing plan had allowed for. Voyager 1 made its closest approach in November of that year, passing something over 100,000 kilometers above the cloud tops, and Voyager 2 followed 9 months later, in August of 1981, on a path that carried it closer still and gave the imaging team a second look at features they had spent the intervening months arguing about. The planet itself was quieter in appearance than Jupiter, its bands muted and softened by a deep haze that sat above the cloud decks and drained the contrast out of them, so that the belts and zones had to be teased out with color filters and computer stretching rather than simply photographed. Beneath that haze, the winds turned out to be far stronger than Jupiter's, with an equatorial jet blowing at something like 500 meters per second, roughly 4 times the fastest winds measured on the larger planet, and the pattern of those winds did not line up neatly with the visible cloud bands in the way that terrestrial jet streams line up with weather systems. The jets were broad and symmetric between the northern and southern hemispheres, which suggested that they were rooted deep in the planet rather than driven by anything happening near the top of the atmosphere. Radio measurements gave the rotation period of the deep interior as a little under 10 hours and 40 minutes, taken from the regular pulse of radio emission tied to the magnetic field, and that field proved to be very nearly aligned with the rotation axis, tilted by less than a degree, which was unlike Jupiter's and unlike Earth's, and made Saturn's magnetosphere a more symmetrical and more orderly place. The atmosphere was found to hold less helium in proportion than Jupiter's does, a difference that has been taken since as evidence that helium has been settling slowly inward through Saturn's interior, releasing heat as it sinks. The rings, though, were the thing that changed most in the space of those two encounters. From Earth, they had been known as a handful of broad concentric zones separated by a few gaps, and from Voyager they resolved into hundreds of narrow bands, and then, as the resolution improved, into thousands. The A ring and the B ring were not smooth sheets, but sequences of ringlets nested one inside another, some sharply bounded, some fading gradually, some faintly eccentric, so that they were not quite circular. Voyager 2 carried a photopolarimeter, and during its passage it watched the star Delta Scorpii through the rings as the spacecraft moved, recording the flickering of starlight as it was blocked and let through again, and that single stellar occultation resolved structure down to a scale of a few hundred meters, and showed that the fine banding continued well below anything the cameras could separate. Some of that structure could be explained. Where a small moon orbits at a period that is a simple fraction of the orbital period at a given place in the rings, the repeated tug at the same phase piles particles into spiral density waves and bending waves, and Voyager found these waves in the outer A ring in the positions calculated for resonances with the moon's Janus and Mimas, wound tightly like the grooves of a record and propagating outward through the ring plane. The sharp outer edge of the B ring was held in place by a resonance with Mimas, and the outer edge of the A ring by the co-orbital moons just beyond it. Other divisions had no such explanation, and the sheer number of narrow bands remained unaccounted for, since none of the known moons could supply anything like enough resonances to produce them all. Within the Encke gap in the outer A ring, the cameras recorded faint kinked strands, which were understood only years afterward, when a small moon was found in that gap in a careful search through the archived Voyager frames. The gap in the outer part of the A ring that is now named for Keeler was seen as well, and in the broad Cassini division, long taken for empty space, the pictures showed several faint ringlets and a general wash of material, so that it was less a division than a region where the ring was thin. Outside the A ring lay the F ring, a narrow braid discovered by the Pioneer spacecraft and photographed in detail by both Voyagers, and it did not behave as a ring ought to. Voyager 1's images showed it as several separate strands that appeared to twist around one another, with kinks and knots and clumps distributed unevenly along its length, and the appearance of braiding was one of the more discussed results of the encounter. Flanking it, one just inside and one just outside, were two small irregular moons, later named Prometheus and Pandora, and the idea that took hold was that their gravity confines the ring between them, each shepherding the particles away from itself and keeping the whole narrow structure from spreading. A third small moon, Atlas, was found just beyond the outer edge of the A ring, and the tenuous G ring was identified for the first time, along with the very broad and very faint E ring farther out. Across the sunlit face of the B ring, there were also dark radial markings, streaks running outward across the ringlets rather than along them, appearing and fading over hours. These spokes should not have persisted, since the inner edge of the ring orbits faster than the outer edge, and any radial feature ought to be sheared into a spiral within a single revolution. And yet they held their shape, and they were found to move at roughly the rotation rate of the planet's magnetic field, rather than at the local orbital speed. The explanation generally accepted is that they are clouds of fine dust, lifted slightly out of the ring plane by electrostatic charging, held and swept along by the magnetic field. For all this structure, the rings themselves prove to be extraordinarily thin, a sheet spread across hundreds of thousands of kilometers, and yet in places perhaps only tens of meters from one face to the other. The moons were surveyed in the same passes. Mimas carried a single impact crater about a third of its own diameter across, with a raised central peak and walls kilometers high, from an event that must have come close to breaking the body apart. Enceladus, seen better by Voyager 2, had regions almost free of craters and crossed by grooves, a surface that must have been renewed long after the solar system formed, and it orbits within the faint E ring, which invited the thought that the moon was somehow supplying the material. Tethys bore an enormous shallow crater and a valley system running most of the way around it. Iapetus was found to be as dark as tar on the hemisphere that leads in its orbit, and as bright as snow on the other. Hyperion was irregular and elongated, tumbling in a way that did not match the tidally locked rotation of its neighbors. Titan had shaped the whole mission's design because it was known to have an atmosphere, and it was the only place in the outer system where one could be studied from close range. And so the Voyager 1 trajectory was built around a passage within about 4,000 kilometers of it, with the spacecraft threading behind the moon so that its radio signal would pass through the air on the way to Earth. The cameras returned an almost featureless orange ball, a thick photochemical haze with a darker northern hood and layers of detachable haze visible at the limb, and no glimpse of the surface at any wavelength Voyager carried. The occultation and the ultraviolet and infrared measurements did the rest, showing an atmosphere mostly of nitrogen with a few % methane, a surface pressure about 1.5 times that at sea level on Earth, a surface temperature near 94 Kelvin, and traces of ethane, acetylene, hydrogen cyanide, and other products of methane broken apart by sunlight. The radio measurement also fixed the solid radius, which turned out to be smaller than had been supposed, so that Titan lost its standing as the largest moon in the solar system to Ganymede. That passage came at a price, and the price had been accepted in advance. To fly behind Titan, Voyager 1 had to be bent sharply northward out of the plane of the planets, climbing away at something like 35 degrees to the ecliptic, which ended its planetary tour at Saturn and sent it on a straight run toward the outer boundary of the Sun's influence. Had it failed, or had Titan proved uninformative, the plan allowed for Voyager 2 to be sent to Titan instead, at the cost of Uranus and Neptune. It succeeded, and so Voyager 2 kept its options, and its Saturn encounter was aimed to place it on the path to Uranus. As it left, the scan platform that carried the cameras jammed in azimuth, and some planned observations of the departing planet and its moons were lost while engineers worked out that a gearbox lubricant had been starved by long continuous slewing, and for the rest of the mission, the platform was moved more sparingly. The cruise from Saturn to Uranus took 4.5 years, and it carried the spacecraft into a part of the solar system where nearly everything the mission depended upon became harder. At about 19 times the Earth's distance from the Sun, sunlight is a few hundred times fainter than it is at noon on a clear day at home, so the cameras needed exposures long enough that the ordinary drift of the spacecraft would smear the image, and the engineers answered this by rolling the whole probe slowly during each exposure so that the camera tracked its target, a technique they called image motion compensation. The radio link weakened as the square of the distance, which meant fewer bits could be sent home in a given second. And so a new compression scheme was written on the ground and loaded into the flight data system, one that sent for most picture elements only the difference from the neighboring element rather than its full brightness value, cutting the volume of an image by roughly 60%. On the ground, antennas were joined together and their signals combined, including the Great Dish in the Australian countryside at Parkes, working alongside the Deep Space Network station near Canberra, so that the aperture listening for Voyager 2 grew even as the signal shrank. The geometry of the encounter was unlike anything the mission had done before, and it followed from the tilt of the planet itself. Uranus lies over on its side, its rotation axis inclined about 98 degrees to the plane of its orbit, and its 5 large moons circle in the plane of its equator, so that in the mid-1980s, with the southern pole turned roughly toward the Sun, the whole system was presented to the incoming spacecraft as a set of concentric circles seen nearly face-on. At Jupiter and Saturn, the moons had been strung out along the flight path and could be visited over days, but here the spacecraft flew through the plane of the system almost at right angles, and every close observation had to be fitted into a few hours around the moment of nearest approach, with the scan platform turning from target to target on a schedule worked out years in advance and rehearsed against the memory of the jammed gearbox at Saturn. Closest approach came on the 24th of January, 1986, at about 81,500 kilometers above the cloud tops. The disk itself was almost featureless, a pale blue-green ball whose color comes from methane in the upper atmosphere absorbing the red end of the sunlight that reaches it, and above that atmosphere sat a haze that muted whatever structure lay below. Only a handful of discrete clouds could be found in the images, and by tracking them at various latitudes, the atmospheric scientists measured wind speeds and found that the visible cloud deck at middle latitudes moved faster than the planet's interior. The temperature near the cloud tops settled around 59 Kelvin at its coldest, and the infrared measurements showed the sunlit pole and the pole in darkness at nearly the same temperature, which suggested that heat was redistributed efficiently, or that the seasons at Uranus, each lasting some 20 Earth years, do not reach deep. Unlike Jupiter, Saturn, and Neptune, Uranus radiated almost no more heat than it received, and no substantial internal source could be found. The magnetic field was the first genuine surprise, and it was detected only shortly before closest approach, because it was not where anyone had thought to look for it. The field was there, comparable in strength at the surface to the Earth's, but its axis was tilted about 59 degrees from the rotation axis and displaced from the planet's center by roughly a third of the planet's radius, which is an arrangement no simple picture of a deep, orderly dynamo would produce. The regular rotation of that lopsided field gave the first reliable interior rotation period for the planet, a little over 17 hours. Behind the planet, the rotating and tilted field wound the magnetic tail into a long corkscrew, and within it, Voyager measured radiation belts of trapped protons and electrons roughly as intense as Saturn's, energetic enough to darken methane ice on the surfaces of the moons and the ring particles over geological time. The ultraviolet spectrometer found aurorae near the magnetic poles and a broad glow across the sunlit hemisphere that came to be called the electroglow. The rings had been discovered from Earth in 1977 when starlight winked out repeatedly on either side of the planet during an occultation, and Voyager 2 found 2 more, bringing the count to 11 at the time. They were nothing like Saturn's bright sheets. They were narrow, sharply bounded, and among the darkest surfaces in the solar system, reflecting only a few % of the light that fell on them, made largely of boulder-sized and meter-sized chunks with comparatively little fine dust, and the fine dust that did exist showed up mainly in the single image taken looking back at the rings against the Sun. The outermost and widest of them, the Epsilon ring, varied in width around its circuit and was found to have a small moon just inside it and another just outside, Cordelia and Ophelia, holding its edges in place by their gravity. 10 small moons were found in all during the encounter, dark objects a few tens of kilometers across for the most part, the largest of them Puck at roughly 150 kilometers, which was imaged as a cratered, nearly spherical body, and all of them were eventually named, like the older moons, from the plays of Shakespeare and the poetry of Pope. The 5 large moons proved to be worlds with real histories rather than uniform balls of ice. Umbriel was the darkest and the most heavily cratered, marked near one limb by a bright ring of unexplained material. Oberon was ancient and cratered too, with dark flaws in some of its basins and a peak standing above the limb in one departing image. Titania showed enormous fault valleys hundreds of kilometers long, and Ariel, brighter and younger looking, had a network of broad rifts whose floors appeared to have been flooded and smoothed by something that flowed, though at those temperatures the something would have been an icy slush rather than rock. Miranda, the smallest of the 5 and the one Voyager passed nearest, at about 29,000 kilometers, was the strangest, a body under 500 kilometers across, whose surface was divided into distinct provinces, ancient cratered plains set against oval regions of parallel ridges and grooves, one of them cut by a sharp chevron of intersecting bands, and along one flank a cliff face that may drop something like 20 kilometers, taller than any on Earth. 4 days after the encounter, the Space Shuttle Challenger was lost, and the world's attention turned away from Uranus while the data continued to arrive. A brief burn of the thrusters set the spacecraft on the last leg, and 3.5 years later, on the 25th of August, 1989, 12 years after launch, Voyager 2 passed about 5,000 kilometers above Neptune's north polar cloud tops. the closest approach to any body of the whole mission. The closeness was deliberate, chosen so that the planet's gravity would bend the path southward and downward toward a rendezvous with Triton some 5 hours later. By then, the radio signal took just over 4 hours to reach Earth, and the data rate was lower still, so the receiving network was enlarged again with the addition of the Very Large Array in New Mexico and the antenna at Yasuda in Japan working with Parkes, and all of this was done while the spacecraft was listening on a backup receiver whose tuning circuit had failed years earlier, which meant every command had to be sent at a frequency calculated in advance to allow for the spacecraft's temperature and its motion. Neptune, unlike Uranus, had weather that was easy to see. A dark oval, roughly the width of the Earth, sat at about 22 degrees south latitude, ringed with bright companion clouds of methane ice crystals riding above it, and it drifted westward around the planet in a little over 18 hours. A smaller dark spot lay further south, and between them a bright feature moved quickly enough around the planet that the imaging team named it the Scooter. Cloud tracking gave wind speeds reaching something near 2,000 kilometers per hour relative to the interior, mostly blowing westward against the direction of rotation. The fastest winds measured anywhere in the solar system, and driven in part by an internal heat source, since Neptune radiates more than twice the energy it absorbs from a sun, that at 30 times the Earth's distance delivers very little. The magnetic field, once again, was tilted, some 47 degrees from the rotation axis and offset from the center, and its rotation set the planet's interior day at about 16 hours and 7 minutes. The rings, which had been suspected from ground-based occultations, were confirmed and resolved. A broad, faint inner sheet, a narrow ring named for Le Verrier, a diffuse plateau, and the outer Adam's ring, which carried several denser clumps or arcs strung along part of its length, while the rest of the ring remained thin, a pattern that appears to be maintained by the gravity of a nearby small moon. 6 new moons were found, the largest of them Proteus, an irregular dark body about 400 kilometers across that had escaped detection from Earth because it orbits close to the glare of the planet. Triton was the last close target of the planetary mission, and Voyager 2 passed some 40,000 kilometers from it. It orbits Neptune backwards, against the planet's rotation, which suggests it was captured rather than formed in place, and it turned out to be smaller than had been estimated, about 2,700 kilometers across, and correspondingly brighter and denser. Its surface reached about 38 Kelvin, the coldest directly measured anywhere in the solar system at the time, and above it lay a tenuous nitrogen atmosphere with traces of methane at a surface pressure of a few tens of microbars, with thin hazes and streaky clouds visible near the limb. A vast pinkish polar cap of nitrogen and methane ice covered the southern hemisphere, and elsewhere the ground was broken into a dimpled ridged terrain likened to the rind of a cantaloupe with very few impact craters, meaning the surface had been renewed recently. Across the polar cap ran dozens of dark streaks, all trending in roughly the same direction, and in 2 places the images showed narrow plumes rising some 8 kilometers before bending over and trailing downwind for 100 kilometers or more, most plausibly nitrogen-driven upward when sunlight warms the ground beneath a translucent layer of ice. The gravity of Neptune, having been used to reach Triton, had also turned Voyager 2 some 48 degrees below the plane of the planets, and it left with no further worlds ahead of it. By the time Voyager 2 turned away from Neptune, both spacecraft had finished the work they had been designed and funded to do, and the project that continued after 1989 was given a new name, the Voyager Interstellar Mission, with a much narrower set of goals and a much smaller budget. The cameras had nothing left to photograph at close range, and the plan from that point onward was to conserve electrical power, shut down whatever was no longer needed, and keep the fields and particles instruments alive for as long as the plutonium held out, in the hope that one or both probes would live long enough to reach the boundary where the sun's influence gives way to the gas and dust between the stars. There was, however, one image left that some members of the science team had wanted for more than a decade, and it required pointing Voyager 1's cameras back the way it had come. The proposal had been raised as early as the Saturn encounter, and it had been resisted for practical reasons, since aiming a narrow-angle camera anywhere near the Sun risked damaging the light-sensitive tube inside it, and the maneuver would consume time on the ground and attention from a team already stretched thin. The advocacy of Carl Sagan, who had also chaired the committee behind the Golden Records, kept the idea alive, and by the winter of 1990, the argument against it had largely dissolved because Voyager 1's imaging system was about to be switched off in any case, and there was little left to protect. On the 14th of February, 1990, from a distance of roughly 40 times the Earth's distance from the Sun, something over 6 billion kilometers, and from a vantage point well above the plane in which the planets travel, the spacecraft took a series of exposures sweeping across the inner solar system. 60 frames were recorded, and 6 of the planets appeared in them. Mercury was lost in the glare close to the Sun. Mars showed only a thin sunlit crescent that vanished into scattered light, and Pluto was simply too dim and too small for the instrument. Venus, Earth, Jupiter, Saturn, Uranus, and Neptune came through as points of light, each of them a fraction of a picture element across, and the wide-angle frames that provided the context had to be taken with the darkest available filter and the shortest available exposure so that the Sun itself would not overwhelm the optics. Sunlight entering the camera at a shallow angle bounced around inside the lens assembly and laid broad diagonal bands of pale light across the field, and in the frame containing Earth, by a coincidence of geometry, the planet happened to fall within one of those bands. A bluish speck suspended in a shaft of stray reflected light from its own star. The image of Earth was assembled from exposures through separate color filters, and it occupied less than a single pixel, a smear of pale blue about 1/10 of a picture element wide, indistinguishable at a glance from the noise and the artifacts that surrounded it. Nothing on it could be resolved. No continent, no weather, no trace of anything living or built, and the scientific content of the picture was close to nil. Its value was of a different kind, and Sagan gave it a name in a book he wrote some years afterwards, The Pale Blue Dot, which is the name it has kept. The data were transmitted back over the following weeks. The cameras were powered down soon afterwards to save the electricity that their heaters consumed, and they were never used again. In time, the software that operated them was removed from the ground systems, and the flight computers were reprogrammed for other purposes. What remained was a set of instruments that measured things no camera could see: the strength and direction of the magnetic field, the density and speed and temperature of the thin plasma flowing outward from the Sun, the flux of energetic charged particles, and the radio and plasma waves that ripple through ionized gas. These were the instruments suited to the question that now defined the mission, which was where the solar wind ends. The Sun's outer atmosphere is hot enough that it cannot be held down by gravity, and it escapes continuously in all directions as a tenuous ionized wind, moving at something on the order of 400 kilometers per second in the vicinity of the Earth, carrying the Sun's magnetic field stretched out with it. That flow cannot continue forever because the space between the stars is not empty. It contains its own gas, dust, magnetic field, and cosmic rays, and at some distance, the outward pressure of the wind falls to match the pressure of that surrounding medium. Because the wind is moving faster than the speed at which pressure waves can travel through it, the slowing does not happen gradually. It happens at a shock front, called the termination shock, where the flow drops abruptly to subsonic speeds, becomes denser and hotter, and begins to turn sideways, sliding away toward the flanks and the tail of the great bubble it has blown. Beyond the shock lies a thick, turbulent layer known as the heliosheath, and beyond that, the heliopause, the surface where the solar plasma gives way entirely to interstellar plasma. Models had placed the shock somewhere in the range of the outer planets and beyond, but the estimates varied widely, and because the pressure of the solar wind rises and falls with the 11-year cycle of solar activity, the boundary itself was expected to breathe in and out by several astronomical units. Voyager 1 reached it first. In December of 2004, at about 94 times the Earth's distance from the Sun, its instruments recorded the signatures of a shock crossing, a jump in the magnetic field strength, a change in the population of energetic particles, and the abrupt appearance of the hotter, slower, more disordered plasma of the sheath. The interpretation was harder than it might have been, because Voyager 1's plasma spectrometer had failed in 1980, so the speed of the wind could not be measured directly and had to be inferred from the behavior of charged particles and from the faint radio emissions that plasma produces. Voyager 2, traveling more slowly and in nearly the opposite direction from the Sun's motion through the galaxy, crossed the shock in August of 2007 at about 84 astronomical units, and it crossed it more than once within a few days because the front was moving back and forth across the spacecraft. Its plasma instrument still worked, and it measured the slowing of the wind directly, finding the plasma beyond the shock cooler than the models had predicted, which suggested that much of the energy of the crossing had gone into accelerating a small population of particles rather than heating the bulk of the gas. The heliosheath took years to traverse. As Voyager 1 pushed deeper into it, the outward speed of the plasma dropped until around 2010, the radial component of the flow had fallen essentially to zero, leaving a broad region where the wind neither advanced nor obviously turned aside in the expected way. Then, over a matter of weeks in the summer of 2012, three things changed together. The count of low-energy particles originating in the Sun's own environment fell away almost completely. The flux of galactic cosmic rays from outside rose sharply, and the density of the surrounding plasma increased by a factor of several dozen. The density was not measured at the time, since the plasma instrument was long dead. But in the spring of 2013, a burst of activity on the Sun reached the spacecraft and set the local plasma ringing at its natural frequency, and that frequency, recorded by the plasma wave receiver, gave the density directly. Working backwards, the crossing was dated to the 25th of August, 2012, at about 121 astronomical units. Voyager 2 crossed the same boundary on the 5th of November, 2018, at roughly 119 astronomical units, and because its plasma spectrometer was still functioning, it watched the solar wind slow and stop across a transition only a fraction of an astronomical unit thick. In both cases, the direction of the magnetic field beyond the boundary turned out to be closer to the direction inside it than most models had anticipated, which implied that the interstellar field is draped around the heliosphere in a way that leaves the two aligned along the spacecraft's path, and both probes continued outward at their fixed speeds into a medium that no instrument had ever sampled from within. The signal that carries all of this back to Earth begins as a few tens of watts of microwave power, comparable to the draw of a small household lamp, fed into the spacecraft's dish and aimed at a planet the spacecraft cannot see. Radio waves spread as they travel, and although the dish narrows the beam to about half a degree stretched across 20 billion kilometers, becomes a cone tens of millions of kilometers wide by the time it reaches the inner solar system. So Earth intercepts only a vanishingly small slice of what was sent. What arrives at the top of the atmosphere and then at the surface of a receiving antenna is a power of roughly a billionth of a watt, and it is spread thinly across the whole aperture of whatever dish happens to be pointed in that direction. There is nothing to be done about the loss. It is simple geometry, and the only remedy available on this end is a very large collecting area, a very quiet receiver, and a great deal of patience. The collecting is done by the Deep Space Network, 3 complexes of antennas placed at roughly equal intervals of longitude around the planet, one at Goldstone in the Mojave Desert of California, one in the hills west of Madrid, and one at Tidbinbilla in a valley outside Canberra. The spacing is deliberate, since a spacecraft in deep space stays essentially fixed against the background of stars while Earth turns beneath it. And 3 stations 120 degrees apart guarantee that as one loses a target below its western horizon, another has already brought it up in the east. The complexes are unstaffed for much of their routine work, controlled from a single operations center at the Jet Propulsion Laboratory, and they divide their time among dozens of missions scattered from lunar orbit outward. So a Voyager pass is a scheduled block of hours negotiated against the needs of everything else that needs listening to. At the center of each complex stands a 70-meter dish, the largest steerable antenna the network has. All 3 began life smaller, as 64-meter antennas built in the 1960s for the early planetary missions, and all 3 were enlarged in the late 1980s, specifically with the Neptune encounter in mind, since the flux arriving from Voyager 2 at 30 astronomical units would be roughly a quarter of what had come from Saturn, and every square meter of surface mattered. Around each 70-meter dish sit several 34-meter antennas, and their signals can be combined electronically, phase by phase, so that 2 or 3 or 4 dishes act as one larger one. That technique of arraying was pushed hard during the outer planet encounters, when the Parkes radio telescope in New South Wales was linked with Canberra for Uranus, and the Very Large Array in New Mexico was linked with Goldstone for Neptune, borrowing radio astronomy's largest instruments for a few weeks of planetary work. The receivers themselves are built around the problem of noise. Every warm object radiates, including the atmosphere, the ground around the antenna, the metal of the dish, and the amplifier's own electronics, and against a signal of a billionth of a watt. That background is not a nuisance, but the whole difficulty. The first stage of amplification is therefore cooled with liquid helium to a handful of degrees above absolute zero, so that its contribution of thermal noise is smaller than the sky's, and the frequency standards that tell the receiver where to look are hydrogen masers, stable enough that the expected frequency can be predicted in advance to a small fraction of a hertz. That prediction matters because the spacecraft's transmitted tone is Doppler shifted by the relative motion of two bodies, neither of which is standing still, and the receiver must be told where in the spectrum to place its very narrow window. Once locked, the same Doppler measurement becomes data in its own right, a running record of the spacecraft's velocity along the line of sight, accurate enough to have contributed to the measurement of planetary masses during the flybys. Even with all of that, the returning stream is thin. Science data now comes down at 160 bits per second, and at times at 40, rates that would have seemed slow in the 1970s and are slower still against anything familiar today. And the information is wrapped in error-correcting codes so that a bit lost to noise can be reconstructed from its neighbors rather than corrupting a whole record. A single measurement of the magnetic field, or a spectrum from the plasma wave receiver, may take many seconds to arrive in full. The result is not an image or a stream of pictures, but long columns of numbers describing fields and particles, delivered slowly and steadily, hour after hour, for as long as an antenna is looking. Voyager 2 adds a constraint of its own. Its close pass over Neptune's North Pole in 1989 bent its path sharply southward, and it has been heading below the plane of the planets ever since, so from Earth it sits far into the southern sky. Northern Hemisphere antennas simply cannot see it. That leaves the 70-meter dish at Canberra as the only antenna in the world capable of sending it a command. And in early 2020, that dish was taken out of service for close to a year for the replacement of its transmitters and other aging parts. Smaller southern antennas could still gather the downlink, so the spacecraft's data kept arriving throughout. But for those months, nothing could be said to it, and it ran on the instructions already stored in its memory until the larger dish came back online and the first new command was acknowledged. Distance also removes any possibility of real-time control. A radio signal takes something over 22 hours to reach Voyager 1 and the same time to return, and roughly 19 hours each way for Voyager 2, so a question asked in the morning receives its answer nearly 2 days later. Nothing can be corrected as it happens. Operations therefore work by stored sequences, sets of instructions uploaded weeks or months in advance and executed against the spacecraft's own clock, with the ground team reasoning ahead about what conditions the probe will find itself in and what it should do if something goes wrong. The uplink is generated at many kilowatts from the 70-meter transmitters, an enormous power compared with the returning whisper, and even so it arrives at the spacecraft as a faint thing that the onboard receiver must pick out of its own noise. The computers waiting at the far end belong to the era that built them. Each probe carries 3 pairs of them, for command, for data handling, and for attitude control, with memories measured in a few thousand words rather than in megabytes, and they are programmed in the assembly language written for those particular machines, a language with no descendants and no modern compiler. Commands are still assembled instruction by instruction, checked against ground test beds and against paper documentation written in the 1970s, some of it by engineers who have long since retired and who are occasionally consulted about why a particular routine was written the way it was. The team responsible has been small for decades, and much of its work consists of reading old memos carefully. That flexibility has been used repeatedly. The image compression scheme that made the Uranus encounter possible was written and loaded years after launch, and the spacecraft have been reprogrammed many times since to work around failed components, to conserve power, and to manage thruster wear. Late in 2023, Voyager 1 began returning telemetry that made no sense, patterns of repeating bits with no recoverable content, and over several months the cause was traced to a single failed section of memory in the flight data system, a few % of the total, which happened to hold code the spacecraft needed. The solution was to move that code, piece by piece, into working areas of memory too small to hold it whole, adjusting the references so that everything still pointed where it should, and then to send the whole rearrangement across 24 billion kilometers and wait most of 2 days to see whether the machine still worked. It did, and the numbers resumed their slow arrival. The power that makes all of this possible declines on a schedule that was known before launch and has held to it closely. Each spacecraft draws its electricity from the heat of decaying plutonium, and plutonium of that particular isotope loses half its atoms in a little under 88 years, so the heat itself fades slowly, while the thermocouples that turn heat into current degrade rather faster. Together, the two effects have taken the output from something over 400 watts at launch down to less than half of that, falling by roughly 4 watts with every year that passes. 4 watts is not much in absolute terms, and yet the entire remaining spacecraft runs on a budget so thin that every subtraction has to be paid for by switching something off. And by the middle of the 1990s, there was already less power available than the full instrument complement needed. So the instruments have gone dark one at a time, in an order worked out long in advance and revised as circumstances changed. The imaging systems were the first to go, since there was nothing left to photograph, and their heaters were allowed to cool until the optics froze into positions from which they could not usefully be recovered. The infrared and ultraviolet spectrometers followed, and the scan platforms that once swung to track moons were locked in place, and in recent years the fields and particles instruments themselves, the ones designed precisely for the environment the probes now occupy, have begun to be retired as well. Engineers have kept them running longer than the power budget strictly allowed by drawing on a reserve of voltage that had been held back as a safety margin, and by switching off heaters in compartments whose contents then continued working at temperatures far below anything they had been tested for, which was a matter of some surprise to the people who had expected them to fail. The other consumable is hydrazine, the propellant for the small thrusters that keep the dish antenna aimed at Earth. Every attitude correction is a brief puff of gas, measured in fractions of a gram, and over almost 50 years, the thruster tubes have gradually accumulated deposits of silicon dioxide from a rubber diaphragm in the fuel system, narrowing the passages through which the propellant must flow. There are redundant sets of thrusters, and the team has rotated between them to spread the wear, and has also allowed the spacecraft to drift a little further off target before correcting, so that fewer pulses are needed. On present estimates, the fuel will outlast the electricity, which means the end will come as a power failure rather than as a loss of control, and the last thing to be switched off will most likely be the transmitter itself, either deliberately or because there is no longer enough current to raise its voice. After that, the two probes continue exactly as they are, since nothing in space slows them. They are already past the point where the Sun's gravity can meaningfully change their speed, and each carries a velocity relative to the Sun of roughly 17 and 15 kilometers per second, the faster of the two being Voyager 1, which received the larger push at Saturn. In the units astronomers use for the outer solar system, that comes to something over 3 of the Earth's orbital radii every year. So the distances mount steadily and unremarkably, and the spacecraft cross in a decade a gap it would take light rather less than a day to bridge. Without pointing, the dishes will drift away from Earth. The spacecraft will settle into a slow tumble driven by nothing more than the tiny talks of sunlight and the residual asymmetries of their own shapes, and they will pass out of the region where anything made on Earth has ever been. Ahead of them lies the Oort cloud, or at least the region where the Oort cloud is thought to be, an enormously diffuse shell of icy bodies loosely bound to the Sun. The probes will take something like 300 years to reach its likely inner edge and tens of thousands of years to pass through its outer reaches, and in all that time, the chance of coming near any single one of its members is negligible, because the objects are separated by distances comparable to the width of the whole planetary system. The cloud is a statistical entity rather than a place one arrives at. There will be no crossing to notice, no boundary marked in the data, and by then there will be no data. The stars they are aimed at are not destinations in any useful sense. Voyager 1 is climbing north of the plane of the planets in the general direction of the constellation Ophiuchus, and Voyager 2 is heading south towards the constellations Telescopium and Pavo, and the two trajectories diverge by well over 100 degrees. Because the stars themselves are moving, the encounters that matter are not with the stars that presently lie along those lines, but with whatever happens to be passing through that part of the sky at the appropriate time. In about 40,000 years, Voyager 1 is expected to pass within roughly 1.5 light-years of a small red dwarf catalogued as Gliese 445, a star currently in the northern constellation Camelopardalis that is itself moving towards the Sun and will be considerably nearer to us then than it is now. Around the same era, Voyager 2 is expected to pass within a comparable distance of Ross 248, another dim red dwarf, this one presently in the direction of Andromeda and also approaching. 1.5 light-years is a close approach only by the standards of interstellar space. It is more than 300 times the distance from the Sun to Neptune, and from that range a red dwarf would appear as a moderately bright star, and nothing more, without measurable warmth, without any tug worth speaking of. Later passages have been calculated in the same spirit. Voyager 2, in something like 250,000 years, will pass a few light-years from Sirius, which is a genuinely luminous star and would be a conspicuous object in that spacecraft's sky if there were any instrument left to see it. These figures are projections rather than predictions. Since the motions of individual stars are known only to a certain precision and small uncertainties grow over such intervals. But the general picture is secure enough. The probes will thread through a region so empty that near misses are measured in light years. Neither spacecraft is leaving the galaxy. Both are far too slow for that, and both are now essentially in orbit around the center of the Milky Way, carried along with the Sun and its neighbors in a circuit that takes on the order of 230 million years to complete. Their paths will diverge slowly from the Sun's, and after a few galactic orbits, they will be lost among the stars of the disk, indistinguishable in their motion from any other small body drifting in the same current. What will happen to the material itself is a question with a wide answer. Interstellar space is not empty of matter, and both probes will be crossed continually by cosmic rays and struck now and then by grains of dust. But the density of that dust is so low that erosion proceeds at a rate that is difficult to measure and easy to underestimate. The aluminium structures, the titanium fasteners, the boom that carries the magnetometer, all of it is cold and unoxidized and under no mechanical stress, and there is no chemistry available to attack it. Estimates for the survival of the gold-plated record, which is copper beneath a layer of gold and mounted in an aluminium cover, run into the hundreds of millions of years and beyond, on the assumption that no particular impact happens to shatter it. The cover carries a small electroplated patch of uranium, placed there so that anyone who found it could compare the amount of the parent element with the amount of its decay products and work out how long the disk had been traveling, and uranium of that kind halves itself in something like 4.5 billion years, which sets the scale on which the makers were thinking. The instruments will be silent long before, and the plutonium spent, and the paint faded from a sun that has become one star among many, and the two objects will go on at their fixed speeds, cold, unpowered and intact, for a very long time. We are going to stop here. The music will carry on for a while, and then it will fade on its own. There is nothing more to do tonight. Rest well and see you very soon.